We're going to kind of break down, I decided we're going to just take a look at the most basic things. A lot of vocabulary we need to know, a lot of concepts we got to understand. The first thing is, what even is a function? Well, a function is a relation between a set of x values. Anyone remember what we call the set of x values? Yeah.
Domain.
Domain, good.
Expansion.
I'm going to call it, not domain expansion, I'm going to call it, we'll get to domain in a second, but my x values are going to be called inputs. Everybody say inputs.
Input.
Okay, input. In our warm-up, the x values are what we put in to the equation. We worked everything out, and then we got out a y value. That's going to be my outputs. All right? And we know that we have a function when each input has exactly one unique output. This always gets really confusing for us because we forget if it's an input that needs one output or if it's an output that needs one input. It gets really, really messy. So we're going to try and break it down today in a couple ways that make sense. All right. One way that we could represent a function is with a mapping diagram. Everybody say mapping diagram.
Mapping diagram.
Okay, it's a diagram where we map our inputs to our outputs. So over here on the left is going to be my inputs. On the right is going to be my outputs. Give you guys a second to write your inputs and your outputs. For both mapping diagrams, we're going to take a look at an example and also a non-example. So we're used to seeing functions as a graph. We're used to seeing functions maybe on a table, but not so much on mapping diagrams, okay? Here's what a mapping diagram can look like. Let's say I've got inputs of 1, 2, and 3. And let's say I've got outputs of, let's keep it simple, 4, 5, and 6. All right? And where the mapping comes in is with these little arrows. I'm going to see an arrow from 1 to 4. That tells me that for whatever function I'm dealing with, an input of 1 would give me an output of what? 4. If I draw an arrow from 2 to 5, that tells me that an input of 2 gives me an output of what? 5. And an arrow from 3 to 6, input of 3 gives me an output of 6, right? Give me a thumbs up if that makes sense so far. Pretty straightforward, right? So this, I'm going to keep this up for Kai. This is a function because each input has exactly one unique output. My 1 puts out a 4, my 2 puts out a 5, my 3 puts out a 6. All right? Any questions on that first one? Okay, let's take a look at the opposite. Let's say I've got inputs of 1, 2, and 3. And this is basically just like a table, right? Like the table we saw in the warm-up. It's essentially the same thing. It's just drawn a little bit differently. Let's say I've got inputs of 1, 2, 3. I've got outputs of 4, 5, 6, 7. I'm going to draw an arrow from 1 to 4, from 1 to 5, from 2 to 6, and from 3 to 7. So get that copy down real quick and then we'll talk about it. If I have an input of 3, what's my output going to be? 7. If I have an input of 2, what's my output going to be? 6. If I have an input of 1, what's my output going to be?
4 and 5.
4 or 5. Is that one unique output?
No.
No. This is not a function. Because the input of 1 has different outputs. Again, this is kind of a difficult thing for us to kind of visualize. Right? So let's think about it in some terms that we may understand a little bit better. Anyone in here like to bake at all? I do. I love baking. I love cooking. Anyone ever used an oven before? Okay, good. Whether you liked it or not, we've all used an oven before. I'm going to draw my little oven. Okay, there's my oven, all right? This oven represents my function. What function does an oven have? Baking, cooking, heating, those things. Yeah, you guys know how ovens work. So this oven is my function, right?
Yes.
Let's say I go ahead and I input a tray of cookie dough.
Cookies.
Okay? All right? So my input is cookie dough. All right? I put them into the function oven, right? What's my output going to be? Cookies. Baked cookies, right? I'm going to make them bigger so you know that they're baked. Because for anyone that's made cookies before, you know. They start out as like little balls of dough and then they expand out. And we'll make them hot. They're sizzling. They just came out of the oven. All right? So my input of cookie dough goes into the function. My output is cookies. Give me a thumbs up if you follow that logic. Make sense? Good. Okay. What if I had, here's my little function oven. Okay. If I input, again, I'm going to input cookie dough. All right. I'm not going to do the, well, I'll do the dots. Fine. Okay. If I input cookie dough, what's my output going to be? Cookies. Is my output ever going to be a cake?
No.
No.
Unfortunately not.
Right? There's my cake. Okay? So check it out. This is how we can think about it, right? Every input needs one unique output. I can't put the same thing into an oven and get a different dessert out. Does that kind of make sense?
Yes.
If I put cookie dough in, I'm only going to get cookies out. Okay? I'm not going to put cookie dough in the next time I come around to bake, and all of a sudden there's a cake or there's brownies in there. Okay? So that's kind of what we're looking for with a function. I can't put a 1 into this function and get a 4 and a 5 out. That would not be a function. Okay? How are we feeling about that so far? Make sense?
Yeah.
Ooh, 5 people that make sense for it? Quick show of thumbs make sense? Okay, good. Let's move away from mapping diagrams. Let's take a look at the vertical line test. Okay, the vertical line test. This is for if we have a graph. So we got 3 different graphs here. They're all a little funky looking. What type of graph do you see in this first one? Continuous or discrete?
Continuous.
Continuous. Does it go on forever?
No.
No. How do we know it doesn't go on forever?
No.
There's no arrows. What does my line end with?
2 dots.
Points. Right? If we end at a point, that's the end.
Yes.
So it's continuous in the sense that I can connect all my points with a line, but it doesn't go on forever. What about this second one? Continuous or discrete?
Continuous.
Continuous. I see a line, that's continuous. What about this third one?
Discrete.
That one's going to be discrete. Okay? So on the top, let's go ahead and write, just so we remember. Continuous. Continuous. Discrete. Okay, just to help our visualization. Now, not all 3 of these represent a function. Now, I don't have the luxury of seeing a mapping diagram with 2 arrows coming from an input, right? So I'm going to use what's called the vertical line test to figure that out. To do that, all we have to do is try and draw a vertical line that intersects a graph. Draw a vertical line that intersects a graph in 2 places, I think is what? Yeah, in 2 places. That's what I meant to say. It was like the space doesn't look big enough for that, but I fit it. A vertical line that intersects the graph in 2 places. So let's take a look at this first one. All right, and what I usually like to do Do you guys have ID cards? Yeah. Go ahead and take your ID cards out.
Oh my god.
You can put it face down so no one sees your picture. I see your picture everywhere.
Wow, it looks so bad, bro.
Why are you showing it? It's so bad, bro.
I look so bad, bro.
It's all right if you look bad. It's your middle school ID card. You're gonna look bad. Okay.
Whoa.
All right. Here's what we're gonna do with our ID cards.
Yeah.
We're gonna take a look at this first graph. All right. And we're going to conduct the vertical line test. It's very simple. You're going to hold your ID card like this, okay, on the left side of your graph, and you're going to slide your ID card all the way over to the right. So the vertical line is this edge of my ID card right here. And I'm going to follow this function. I'm going to go all the way over. What?
Exposed.
No,
What is that?
it's me.
If we all look at
What grade was
It's me.
that?
8th grade. It's right here.
You have the same haircut.
Thank you. I think
the same haircut.
it's a little longer in that picture, but it's not about me. It's about the line test, okay? So you're going to drag your ID card. You're going to go all the way across, and you're looking for any point where you see 2 points directly above each other. I know that might not make sense on this first one, but it looks like this first one passes, okay? What I'm looking for in this second graph, this is where we can see that it does not pass, okay? If I'm sliding this over, oh, look at that. I can draw a vertical line from one point on my line to the next. From there to there. I can keep going. Look at that. I can draw a vertical line from that point to that point on that funky looking line. I could even keep going and draw another vertical line. Boom. From that point to that point. You see all those vertical lines?
Yep.
Right? That means that this is not a function. It did not pass the vertical line test. Now that we see what it looks like to not pass, if I go back to my first one, is there any point on this graph where there's 2 dots above each other? No. There's only ever just 1 dot along this vertical line. Sometimes it gets a little close, but they're not directly above each other. So that makes this one a function.
Discrete. Data function.
It's still continuous, right?
Yeah.
Now let's look at this last one. Now there's not a line for us to follow, but we're still going to drag our ID card across from left to right, and we're looking for 2 points on that same vertical line. See if you can find any. Tristan, you found 2? Can you see the numbers on this graph? Probably not, right?
I found one.
I found one too.
You found one? What X value, if you could see on your graph, what X value did you find those 2 points at? -2. Boom, right there. Point. There's a vertical line. Is there any other ones? Nope. But it only takes one. It only takes one for this to not be a function. All right? So my first one was nice and clear. It is a function. My second and third are not a function. Off to the side, let's explain, thinking about our mapping diagrams, why is this last one not a function? Well, these 2 points here, what are the coordinates of this top point here? -2, comma, what is it, 6? Yeah, -2, comma 6. What are the coordinates of this point down here?
-2, comma 5. -5.
-2, comma, -5. Right? That's these 2 points. I'm going to do a little arrow. So what do I have here on these 2 points? I have the same input, right? I've got cookie dough and cookie dough. But when I put them in, one time I got cookies, the next time I got a cake. That does not make sense. That is not a function, right? My inputs do not have one unique output. This time they have 2 different outputs, right?
Yeah.
So it's the same idea as a mapping diagram, just presented in a different way.
Yeah.
But either way, what we're looking for is repeating inputs with different outputs. All right? If I had something like, if I had a graph like this, give me a thumbs up if you think that is a function. Give me a thumbs down if you think that is not a function. What do you think? Good, I see all thumbs up. Again, vertical line test. I slide this over, boom, boom, boom. I'm still only looking at 1 point, 1 point, 1 point. There's never a point where I have 2 points on the same vertical line. Yeah. Okay. What about this graph? Thumbs up for function, thumbs down for not a function. Good, our thumbs should definitely be down on this one because look, boom. There's 2 points on this line, on the same vertical line. There's 2 again, there's 2 again, there's 2 again, there's 2 again. This one failed miserably, right? So that would not be a function. Give me a thumbs up if that makes a little bit of sense. Cool.
So we just have to find which is a function and which is not?
Yes. Well, that's the beginning. Now we'll talk about domain and range, like we kind of mentioned yesterday. But we know that. What do you mean? This is the second one. There's only 2. Would you rather write your notes by hand?
Yes.
All right. It's kind of hard to write all the graphs, but
We have grid paper. Imagination,
this stuff is easy, right?
Wait, you have the same period? Okay. How come I have never noticed you even once? Kind of sounds good. Well, that 2 miles is so long.
Yeah, I know, right?
My leg was so sore.
What time did you get?
Like 29 minutes. I missed it.
I got 26, bro.
I pushed back.
He knows. He's muted. And then he got caught.
Oh, we do have a homework assignment. I was trying to think. Everybody got it glued in? Yep.
Yes.
Perfect. Let's get started. So now we're going to look at some tables. These look very similar to our mapping diagrams, except there's no arrows, right? Because my input and my output are on the same level. Over here, we had a little bit of overlap, right? We didn't write 1 twice, even though it showed up as an input twice. Over here, we do have 1 written twice. That's all. That's the only difference, but it's basically the same thing. So we're going to determine if these represent a function or not. What are my inputs in this first table?
3, -2, 1, and 8.
3, -2, 1, and 8. Perfect. Are there any repeating inputs here?
No.
No, those are 4 unique numbers. So I technically don't even need to look at my outputs because I know this is a function.
Wait, isn't there a repeating? Oh, on that one.
Yeah, we're looking at the first one. There's nothing repeating. Everything's unique. This would be a very ugly graph if we plotted it. It might be discrete, which is okay. Just 4 random dots.
Oh, and open.
Still a function.
Yeah, in the C.
If we plotted these, there would be no dots directly above each other, right?
Yes.
I hate graphs like that.
Okay, for this next one, what are my inputs for the second table?
1, 2, 4, 1.
1, 2, 4, 1. Do we have any repeating inputs?
Yes.
Yes, we do. Look at that. We've got a 1 and a 1. What are my outputs for the first? What's my output for the first one?
6.
What's my output for the second one?
6.
6. Is that a different output?
No.
No. So that's still a function.
Oh, really?
Even though we have a repeating input, it's the same output. Cookie dough gives me cookies. Cookie dough still gives me cookies.
What about the other numbers?
These other numbers?
Yeah.
4 cookie gives you 6.
But then you have
Yeah,
the
but-
2 1s.
2 is equal to
You have 2 1s, Tyler, but they have the same y. Now, if you're asking, well, 2 can give me 6 and 4 can give me 6 as well, right?
Yeah.
Wait, I have a question.
Sure.
So if the first one, if as long as there's
Oh, wait.
if there's 2 1s and there's 2 6s, it's gonna be a function.
Yes. If
Yes.
they're equal to each other.
Oh.
Because look, over here we had 1 going to 4 and going to 5. We can't have different outputs. Here I have a 1 going to 6 and a 1 going to 6. Is that the same point?
Yes.
Yeah. It's the same exact point. Now you may be looking like, oh wait, all my y's are the same. That's a repeating, and I've got different inputs. It doesn't work both ways, right? It's fine for us to have repeating outputs. Let me show you why. If I were to graph all these points, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay, I'm going to graph all these points. 1, 6, 1, 6, 2, 6, 2, 6, 4, 6, 4, 6, 1, 6 again. That's the same point. Let's say it's discrete. We don't even have to connect them. Does this pass the vertical line test? Yes, it does. Right? Even though it's a flat line, it's still a function because it passes the vertical line test. Right?
What year is the ID card from?
I don't know. I don't remember. It was too long ago.
2000?
For my last one, everyone good on that second one? Because that one I tried to trick you guys. Does that make sense though? Okay. For my last one, what are my inputs?
1, 1, 2, 3.
My inputs are 1, 1, 2, and 3. What are my outputs?
8, 7, 6, 5.
8, 7, 6, 5. Do I have any repeating inputs?
Yes.
Yes, I do. Do they have the same output? No. Is my third table a function?
Nope.
Nope. Because if I put a 1 in and got an 8 out, I can't then put a 1 in and get a 7 out. Okay? Again, just think about the cookie dough metaphor. Think about each of these rows as a different day, right? For my middle one, on Monday, I put in cookie dough and got out cookies. On Thursday, I put in cookie dough and got out cookies.
Yes.
My oven is functioning properly.
Hooray.
Here, on Monday, I put in cookie dough, got out cookies. On Tuesday, I put in cookie dough, got out brownies. My oven is clearly not functioning within the, confines of our reality, so something must be wrong. It's not a function. What's that?
Sounds like the oven got an upgrade if we put a cookie dough got out.
Yeah.
Unless you really wanted cookies, and then you open it up and all of a sudden you've got brownies.
Yeah, but
That'd be pretty
You
disappointing.
get like different. You get
We're not going to argue about desserts, okay?
Yeah, but
We've got
you get
math to learn.
different desserts at a time, so it's like gourmet, like
So underneath this, we're going to write input of 1 had outputs of 8 and 7. Okay, and we cannot have the same input with a different output. But this is where it gets confusing. Because according to this middle table, we can have different inputs with the same output. See how easy it is to get confused? Different, same input, output. The more practice we get, the more sense it'll make. Any questions I can answer about that?
No.
Thumbs up if you're still with me, still doing good. Perfect. Last but not least, domain and range. I'll leave that there for a second so you can write. Our domain, like we said, is the set of inputs. Are inputs X or Y?
X.
X. So the domain just represents what X can be. My X can be 1, it could be 2, it could be 3. My range is the set of outputs, which is what Y can be. Like we saw yesterday, my, was it number of vacuums? Is that what we were selling?
Yeah.
Yeah. My domain, I could have sold 1 vacuum, or sorry, 0 vacuums, 1 vacuum, 2 vacuum, all the way up to 10. My range, I could have made $0, $20, $40, $60. It's all the Y values accepted by the function. Now, we've only talked about discrete domain and range. Now we're going to learn about continuous domain and range too. Here's a continuous function. How do we know it's continuous?
Because it has lines.
There's a line right away. We see a line. No matter how funky and weird the line is, it's continuous. All right? So for my domain, I'm going to do my little squiggly arrow. And this is where it's going to be a little bit different because this is a continuous function, okay? What's the smallest X value you see on this line, Liana? -5. Go ahead and draw a line. You guys have highlighters in your supply boxes? Okay, perfect. Doesn't matter what color. Take a highlighter and draw a vertical line at -5. Actually, you have 2 colors. Everyone take out 2 highlighters. You should have 2 different colors. If you have your own, even better. We're going to make a nice visual here. What's the largest X value on this graph?
6.
+6. I'm going to do my other line right there in the same color. Here's how we're going to write the domain. Because this function can accept more than just -5, -4, -3, -2. I could also find a point in here, -3.5. I could splice it again, -3.25, 3.15, 3.10658, right? It's an infinite number of points on this line. So the domain is from -5 less than or equal to, right? Because it can equal 5.
Yeah.
X less than or equal to +6. It wouldn't, we couldn't physically write all of the possible inputs for this function because we could keep cutting down the decimals forever and ever and ever and ever. It would be literally impossible. So we can sum it up. My domain, I can have any inputs, right? X is my input. Any inputs greater than or equal to -5 or less than or equal to 6. Basically anything between -5 and 6, but including -5 and 6. That's why we got to put the little equal on the bottom. Give me a thumbs up if you see why we write it that way. Ooh, okay, a lot less people. Maybe with the range it'll make sense. With your other colored highlighter, we're going to ask ourselves, what's the smallest Y value on this function, Alex?
-3.
-3. I'm going to do a line down here at -3. What's the largest Y value on my function? Tia? 8. So this function ranges between -3 and 8 on the y-axis. Right?
Yes.
So my range is going to be -3 less than or equal to what?
X.
X?
Y.
Y. Range, we're looking at the y values. Right? Range is the set of outputs, what y can be. Y can be anywhere from -3, including -3, all the way up to what? 8. Okay? And this is called set notation. Set notation. A set of inputs and a set of outputs. It's the set of inputs from -5 to 6, the set of outputs from -3 to 8. So it's kind of like we're just boxing in our function. How far can I go on the y-axis in blue? How far can I go on the x-axis in orange? If I were to have, this isn't going to matter necessarily, but if I had a line like this, right? How far can I go on the x for that line? What do those arrows mean again? Goes on forever.
So infinity.
-infinity all the way to
X.
positive infinity. Because this line goes on forever. Right?
Just infinity?
What's that?
Could you write like just infinity?
It's from -infinity to positive infinity. So infinite number of spaces in the negative direction, infinite number of spaces in the positive direction. That's right. Now for a discrete graph, we kind of already did this, so this will be a quick little review. For my domain, again, that's my x coordinates. What are all the possible x coordinates you see on this graph? Liana.
-2 to -8. Not -8, just to 8.
-2 to -8.
No, 1 to 8.
1 to 8. So inputs are x values, right? So here's a point, I look down, my x value is 1. Here's a point, I look down, my x value is 2. I've got 3. I've got 4. I've got 5. All the way down, I've got 6. Any more?
No.
No. But because this is discrete, remember, we have to list them all out. That's what we did yesterday, right? Yeah. 1, 2, 3, 4, 5, 6. That's what it was like on your Alex assignment, right? I think? Okay.
I think so. Sound like that.
Right?
Yes.
Because there is no point at 1.5, at 1.25, at 1.1, at 1.05. There's only a point at 1, a point at 2, a point at 3, a point at 4. Now, what are my y values for all these points? -1, right? We're looking over. -1. I've got a 0, 1, 2, 3, and 6. So, -1, comma, 0, comma, 1, 2, 3, 6. And that's still set notation. Basically, those squiggly brackets, that's set notation. Was this too much at once?
No, I kind of
Perfect.
Wait.
Kind of.
Way too much at once?
No.
Oh, okay.
I honestly think it might be nap time.
It might be nap time. I think it might be homework time.
Nap time.
Homework.
I'd rather do homework than take a nap.
I still